Okay, so for my code here, when I get an input of size 1, it's going to take one step. I'm going to hit the base case immediately. And for an input of size n, so a recursive call with input of size n, it's going to do one step, and then it's going to make another recursive call, but this time the recursive call uses n divided by 2, which is written in our racket code as quotient n2. Okay, so I want to unroll this so that I can see what the recurrence relationship's big O runtime that it produces is. To do that, I'm going to make my cheat sheet, and that cheat sheet is just a set of ways of rewriting my recurrence relationship here so that I can find things to plug in. So it's not a transformation in changing it in any meaningful way, but I can just say like, oh, well, if n is n over 2, then I could rewrite this expression as 1 plus t of n over 4. Okay, and those two expressions are equivalent. And I could do another one where n over 4 is equal to 1 plus t of n over 8. And I'll do one more. T of n over 8 is 1 plus t of n over 16. Okay, and my goal here in the unrolling is to get rid of all the t's on the right-hand side. So what I'm going to do is I'm going to start by substituting in that first expression. So t of n is equal to 1 plus, and now instead of writing that t of n divided by 2, I'm going to put this 1 plus t of n divided by 4. Okay, I still have a t on the right-hand side, which I don't want, so I'm going to substitute in that next piece on my cheat sheet. T of n is equal to 1 plus, and now I write 1 plus t of n divided by 8. 1 plus t of n divided by 8. Okay, I think we can keep seeing where this is going, but I'll plug one more in. I see t of n is equal to 1 plus t of n divided by 16. And then I'll plug in a concrete value, so t of 16. In that case, t of n, if n is 16, would be t of 1, so it would hit my base case. So in that case, I would get 1 plus 1 plus 1 plus 1 plus 1. Okay, so that would be 5. I can look at a few more examples to see if I see a pattern. So if I had plugged in 8, I would have hit the base case one step earlier, so I would have gotten 4. If I had plugged in t of 4, I would have hit the base case one step earlier, so I would have gotten 3. For t of 2, I would have hit it one step earlier, so that would have been just 2 steps. We can see again here that the n value, if we thought about that in terms of a balanced binary search tree, if there are 2 nodes in my row, that means there are 2 rows of nodes. If there are 4 nodes in my row, that means that there are 3 rows of nodes. If there are 8 nodes in my row, that means there are 4 rows of nodes. If there are 16 nodes in my row, that means there are 5 rows of nodes. Really, we can think about this t of n, if that's how many nodes there are in a row in a binary search tree, then how many nodes are in among the leaves in a binary search tree, then I know the height of that tree is going to be log base 2 of n. And our calculation here showed that it was just 1 different than our height. So it's log base 2 of n, and the actual value is plus 1. And we could plug in some specific values here, so t of 2 equals log base 2 of 2 plus 1. Log base 2 of 2 is just 1, so that is equal to 2. Let's look at t of 8 is log base 2 of 8 plus 1. And let me remind you of the log rules. So if we have y equals b to the x, then that's equivalent to x equals log base b of y. So here my b is 2 and my y is 8. So we're trying to solve for the x here, imagining I had my y is 8. So I have y equals 2 to the what? And that's what this log is really calculating. I say, well, I know that x here has to be 3, and that means that the log base 2 of 8 is 3. So here I get that this is 3 plus 1, which is what we got there. And if logs seem even a little bit mysterious to you, try playing around with these expressions with concrete values to be like, oh, actually, I understand exponents, so these aren't so bad. It's just an inconvenient way of rewriting them. So in sum, with my recurrence relationship that I've got here, this is in big O of log base 2 of n.